Bayesian network example for underestimating depth diameter age relations, and they're a postdoc at Arizona State University. Prasun, go ahead and take it away when you're ready.
Okay, can you hear me?
Yes, we can, loud and clear. Thank you.
Okay. Hi. So the topic which I'm going to present on is how can we design a simple Bayesian network for understanding depth diameter age relations. I'm going to touch upon why we are starting with this particular relation and what are Bayesian networks in general. And then what I'm going to do for the vast part of this talk is I'm going to try and show how we can use data to actually design a Bayesian network. And with that, we'll conclude with some of what we are planning to do as future work. Okay. So why do we want to start with depth diameter age relation? Number one is that, well, these are actually really simple relationships to study in the beginning, and we can actually really look at craters and we can measure them and observe them with less effort. And these are reduced complexity data sets, and we can use this to compare against the huge amount of work which has been done during the Apollo era. Particularly, if you look up, you'll see that a lot of work has been done in this regard in between 1960s to 1980s, and I think it was led mostly by Pike. And these are definitely useful and important parameters to study, because they would ultimately give us indications about the cratering processes and mechanisms which are in place. Next slide. So this was a slide which I used when we started with this work and was presented in the LPSC conference, where I actually wanted to show that why we need to get into the probabilistic modeling mode. And this is because if you look at the data sets here, so this represents the Apollo era data, which has only about 120 data points. And this is the LARO data, which has 10 times more data sets. Now, what happens here is, if you look at this data, this is equally dispersed in all directions. The data cloud is kind of evenly dispersed. And but this is in the log domain. Now, if we try to model this in a very normal domain, this entire data set, which is 10 times more data points, gets into this small plot which is here. While the Apollo era data set you can see it here. This is because this particular Apollo era data set we're talking about huge craters. And this one, we're talking about really small craters. So what happens is that in order to take into account the dimension of the crater, we have to switch domains between a simple domain, which is easy to understand, to a log domain, which is compressed. And modeling doesn't really happen really well in the log domain. And I'm not going to talk about the problems with the modeling in the log domain, but what I want to say is that instead of modeling the data set itself, what I would like to do is to model the density or the probabilistic distribution of the data. Next slide. The advantages of probabilistic relationships is, number one, because it's probabilistic, it's not deterministic, which means that it does not coerce us into believing some form. It doesn't tell us that, okay, this is according to a straight line and try and fit a line to the data. We just let the data arrange itself based on its own distribution. Secondly, we can use this probabilistic model when it is created to ultimately model and infer deterministic relationship. So suppose if something is actually indeed a straight line, we would find that when it satisfies the relationship of straight line, that has the maximum probability. Thirdly, a model allows the incorporation of additional parameters. Probabilistic models are by nature, they are very flexible. You can add and subtract variables from that model. And when we select the probabilistic model, there are a couple of them which we can select, and I chose to select the Bayesian model because the Bayesian model works on priors, which means that we have already done a huge amount of work so far. Why not use that information to infer something for future work? So all this work which has already been done, and we have already proven a lot of things using simulations, theoretical relationships, why not use that information to infer something new? Because the progress is we should go forward and not contest between different data sets to get to a particular relationship. So we choose a flexible model so that it's easily incrementable, and then we can actually go forward as we get more and more data. Next slide. So Bayesian networks is a compact model representation for reasoning under uncertainty. Now understand this, that whatever observations we are having here, there will be uncertainty. So we are trying to model something which has a particular degree of uncertainty intrinsic within that data set. So we know this, that the things which we are trying to model, they are random variables. And that's why the entities in a Bayesian network, they are random variables. We use a graphical structure to show the interdependency between these variables. And ultimately what we try to do is that we take all these variables which we think can ultimately influence each other, and we try to model them jointly. So we take them together and we try to model them jointly. One important advantage in doing this for Bayesian networks is that Bayesian networks is really robust to missing data sets. And all of us who have worked with creative features would find that when you try to compare different sources of information, something or the other will be missing, and there will be more noise. But Bayesian networks, our probabilistic framework, is robust to that. It allows the idea that some things can be missing. Okay? And when we model this joint probability, we can ultimately get to this conditional probability, which is the most important part, which gives you the sense that given X, what happens about Y. Okay? Now, and the other way of getting the conditional probability is a rule which we know as the Bayes rule. I'd like to point at there is a huge importance to this idea about knowing or belief. That means we are trying to build on something which we already know to be true, or for which we know that it is probabilistically it's going to be a true thing. Next slide. So I'm just going to go through the steps how we can use data to model this Bayesian network. So this is the first step. In the first step, what we just do a scatter plot, and then from here we can actually infer where the data cloud has the maximum density. Now note that since the data cloud has maximum density, we can try and fit a straight line which already intrinsically believes that the standard deviation across that fit is constant. But the Bayesian networks don't allow that. So where the data density is more, you have different standard deviation, and that's why it's more robust. And then using this data, we try to do our joint probability modeling using any kind of model. I've taken the example of a Gaussian mixture model because they are the oldest. So that's why I've started with that. But you can use a beta or a Dirichlet priors, whatever works. And then using that, you get, this is the joint probability model where that is the density. That indicates the density. And you can see that you have a weak correlation here and a strong correlation here. And then using this model, you can infer from the joint probability the conditional probability for different, for how X influences Y or Y influences X. Next slide. So what I use here are these references to build upon the data. And here we have depth to diameter on the x-axis and an age class on the y-axis. The age class has been defined in these references, and they range from the pre-Nectarian to the Copernican. But when I tried to actually find out where these, the different age classes of craters were in terms of population, what I found is that a huge number of craters were really, really old. So if we try to model this thing together, what happens is this intrinsically biases the whole modeling process. What I do is that from this histogram, I find out the data ranges between this depth to diameter, and I redo this modeling by selecting only few samples. So like we select approximately 100 samples from each particular age group, and we try to do the modeling. Next slide. Okay, so if you do this modeling, you'll see that we see three different clusters. Definitely, as you would think, one occurs at age +1, +2, and +3. So we have grouped this between the 6 classes. We have actually grouped 2 adjacent classes together, and this kind of shows the relative intensity of the likelihood of such a particular age class occurring for this particular depth to diameter. Next slide. And once we do this modeling, we can actually use this joint probability So one parameter is depth to diameter, the next one is age, to find out how age influences depth to diameter or the depth to diameter influences age. Next slide. Okay, and then once we have those values, we can fit this into a hierarchical directed network, and we can show if we put these values here. So suppose we know, we know for sure that this is where the depth to diameter is there. Then it means that this particular value is actually equal to 1, and then the conditional probability actually gives you the probability for the age, which means that in this particular range, so there is 85% probability that between these craters like 35 to 100 kilometers, the depth to diameter which falls into this range, that they would be pre-nectarian or nectarian, and that comes from this data set. So as we increase the data set, these results might change a little bit. Okay, next slide. So we try to make this model a little bit more complex now. So we include the optical maturity parameter from the Clementine UV data. Now, optical maturity shows the effect of space weathering, and high values indicate immature materials and low values indicate mature materials. So the method is we find the mean OMAT values from the craters, and we constrain to have the equal number of samples for each age class. Next slide. So we do the same kind of modeling, and this is the same kind of modeling which we did in the previous example. But note that now we have, instead of 2 parameters, we are working with 3 parameters. So now what we do, the color indicates the joint probability of depth to diameter and OMAT conditional to a given age class. So this is the direction, this is the forward direction of modeling. Okay. So, and we know, and since we select equal number of points, we know the probability for each age class is just 1 by 3 because there are 3 age classes. Next slide. And using the previous slide, now what we do, note that we have reversed the direction. We reverse the direction of the probabilistic modeling. So now what we do, that given a depth to diameter and OMAT value, what can we say about the age? And this is where the power of Bayesian network lies. We can predict. Once we have made the model, we can now predict for things which were so far unknown.
1 minute, please.
Well, the conclusion, I'd say that the work done in the polarity is fantastic, but now we need more and more, when we have more and more data, we need to look towards a robust modeling approach. And this robust modeling approach we try to do with Bayesian method of modeling, where which already has a theoretical, rigorous theoretical understanding, and we can relate different domains which are not directly related, and we can predict. So our ongoing work is to actually combine the crater age related information from our current LRO WAC mosaic data. With that, thanks, and I leave the floor open for questions. Thanks.
Great, thank you, Prasun. It's very interesting modeling. And if you have any questions, please go ahead and type them in the presenter window now. I was curious if you could comment on how your model will be affected by LROC and new high-resolution data that's continually coming in. How will that benefit this model and the predictions that you're showing?
Well, this is a work in progress, and we have just kind of scratched the surface for this. But what I would think is going to happen is that the data density is going to be much more stronger. So we would see that some relationships which we have seen previously in different literature, we'd see that some of them are going to actually be proven to be more stronger, and some of them are going to be proven a little bit less stronger. That's what I would, I intend to see.
Okay, great. Thank you very much. If anyone else has any questions for him, please take that into